Okay, hello. So let's start this lecture. So now we will continue with our counting module. And today we will take a look at permutations and combinations when repetitions are allowed. And then along with it, we will look at some problems where you want to distribute objects into boxes. Okay. So let's start with this example. So you want, okay, just try this out. And as usual, just let me know if you are. Yes, so repetition is allowed. Yeah. Yes, so what is the answer? The answer is 26 power r. So how do you see it? So you want to form a word of length r. So at position 1, you have 26 options. At position 2, you have 26 options and so on. So it's 26 into 26 into 26 r times. That gives you 26 power r. Okay. So this is the first uh, uh, remark. So the number of r permutations of a set of n distinct elements when repetitions are allowed is n power r. So when repetitions are not allowed, what was it? So what is the number of r permutations of n distinct objects when repetitions are not allowed?
NPR.
Correct, correct. Yeah, so that is NPR. And now when repetitions are allowed, it is n power r. Okay, so just keep this in mind. So try this example. So 4 power 5 is not a correct answer. Let me also tell you this has nothing to do with the previous question. Okay, with the previous statement. Okay, so let me guide you through this. It's not an easy question. We have not seen this also. So first of all, okay, so the notes of 10 rupee are identical, 20 rupee notes are identical, 50 rupee notes are identical, and 100 rupee notes are all identical. And so you don't get confused by this 5. See, we have to take 5 notes, right? This is to just say that there are enough notes of each kind. That is what this assumption is. So now, in how many ways can 5 notes be selected? Okay, so let's try to see the solution. See, suppose this is a box containing 10 rupee notes. This is a box containing 20 rupees. This box containing 50 rupees, and this is a box containing 100 rupees. Totally, we have to select 5 notes. Suppose I choose 2 tens, 120, 150, and 100. I will mark it like this. I will allocate this space for 10, this space for 20, this space for 50, and this space for 100. So I'm putting 2 stars to denote that I've taken 2 tens, 1 star for 20, 1 star for 50, and 1 star for 100. Now look at this thing. Here I am not taking any tens, I am not taking any 20s, I am taking 3 50s and 2 hundreds. Okay. So each selection of 5 bills can be denoted using a picture of this form. Okay. I can maybe do one more. Like if I take, for example, if I take so 110, 220s, 350s. So 350s. How will that look like? That will look like, first of all, I make space for all of them. So 110, 220s, 350s, and nothing here. I mean, and nothing here. Okay. So the question is now, how many such pictures are there? So this is a sub question. Now find the number of strings which are formed using these bars and stars. The total length has to be 5, has to be 8, because there are 3 bars and 5 stars. Okay. So the question now boils down to find the number of strings of length 8 over bars and stars that contain exactly 5 stars. So what is the answer to this? So first of all, have you understood this picture? Each selection of 5 bills is equal to a picture of this form. Then the question now boils down to counting the number of such pictures. So what does the picture contain? It contains 3 bars, and then you have to distribute these 5 stars somehow here. Okay, so the length of the string is 8 and it contains 3 bars. It can come at any position. Okay, so now what is the number of such strings? I can give you a hint. We did this in the last lecture. The question was, how many bit strings of length n contain exactly r ones? So this is how many, this instead of bits, there's a star and a slash and a bar. Okay. So yeah, many of you have given the right answer, which is, see, in order to find the, do I have, I have tried the answer. So there are in all 11 positions, and to choose 3 positions for the bar. And this can be done in, sorry, there are not 11 positions, there are 8 positions. Sorry. Okay. And we need to choose 3 positions for the bar, and this can be done in 8C3 ways, or which is the same as saying 8C5. You can either choose the bar or the star. Okay, so the final answer is 8C3. Is there any question now? Have you okay, so let me continue. So
Sir,
what is,
one thing.
tell me, yeah. Hello?
Hello.
Yes, tell me.
Yeah, sir. Why is 4 to the power 5 not correct?
How do you get 4 to the power 5?
Because like for every note we have
Okay,
like we
let's
have to choose 5 notes, right?
one
So for the
second.
first place we have 4 choices.
So what is the argument? So,
You are taking notes in order. We don't want an order, I think. That's why.
so let him explain.
Okay, so see, like 5 notes we have to choose. The first note can be chosen in 4 ways. Any of the 4 denominations can be chosen, right?
Okay.
And the second note, the same goes for second, third, fourth,
Yeah.
every
So
note.
okay. So now you understand the other comment just made.
We don't get to choose an order, right?
So what is the meaning of first note?
Uh-huh. Uh-huh. No
Okay,
order. Yeah, yeah.
right? So there is no first note, second note, third note.
Mm.
It's a set of 5 notes. So there's no permutation here.
Yeah, understood.
It's a selection. It's a combination. Yeah.
Mm. Mm.
Okay. Good. Very good. Uh, Notes are not ordered. As in, there is no first note, second note, etc. Okay, good. Okay, yeah, thanks for your question and thanks for the answer. Okay, so let's generalize this.
Sir, one thing. It's
Yeah,
the combination. It's not permutation.
correct.
Okay.
Yes. So this is exactly where I'm coming now. So, so instead of, the first thing, that n power r was for r permutations with repetitions. So now we are looking at r combinations. Okay, so the number of r combinations of n distinct objects where repetitions are allowed. Okay, so I have, so how would I do that? So I have n objects I want to choose R of them, not in any order. I want to choose R of them, but I am allowed to repeat some objects. Okay. So in the previous case, I had what? How many? I had one, two, three, four objects. Okay. And I had, sorry. Okay. I had four objects and I had to choose five of them with repetitions allowed. So, and in order to do that, what we did, we added three bars to denote that object one, object two, object three, object four. So now in the case when there are n objects, you have to draw n minus one bars to say this is for object one, object two, object three to object n. So there are n minus one bars, and then choosing some number of, so choosing one object of type 1 is denoted by a star here. Okay. An object, choosing an object of type 2 is denoted by a star here. You can have several stars, but in all I need to have R stars. Okay. So then the question boils down to finding the number of strings with n minus 1 bars and R stars, and you need to find the number of strings. For that, totally the total length of the string is n minus 1 plus R, and you want to choose R positions for the stars, so you get this value. So n minus 1 plus R, CR. Okay, so it is exactly like the previous question. So when the selection does not depend on the order, but multiple selections of the object are allowed. Okay, let me do an example and then things will. So try this example and then let me know if you have any questions.
Hello.
Yes.
So I have a question regarding the last problem. So can we go back to the question once?
This one, the bill thing. Yeah.
Notes, the problem of
Yeah,
notes.
yeah, yeah.
So here the question says that the notes of different denominations are the notes of same denomination are indistinguishable, but the notes of different denominations are distinguishable, right?
Yes.
Then how can we assign the same color to different same color of stars to different notes of different denominations?
No, but why the color of the star is not important? No. See, this is just saying that I am picking two notes of denomination 10, one note of denomination 20, one of denomination 50, and it's just the number of stars that matter. You understand? See, suppose I tell you I have only denomination 10 and denomination 20. Let me do this. Suppose I have only denomination 10 and 20. Okay, and then I want to pick three notes. How would you do? So what are the possibilities? I can either take three, I can either take 10, 10, 10, all three of them 10, 10, 10, 20, 10, 20, 20, or 20, 20, 20. See, what is this 10, 10, 10? It means that I'm choosing 10 here. I mean, I'm choosing three of tens. If I put 10, 10, 20, it's like saying 10, 20. I'm just giving a different way to picturize the same thing. This one is 10, 20, 20. Okay. And finally, this one is 20, 20, 20. See, the place where the star occurs gives whether it is 10 or 20. The color of the star is not important. Is that
Okay.
clear?
Yes, sir.
Okay. I'll go back to the question. Yeah. Okay, so how do we do this? So shop has 5 different cookies and we want to choose 3 of them. So how are the stars and bars? So I will have 4 bars. This is for cookie 1, cookie 2, cookie 3, cookie 4 and cookie 5. And then we have to choose 3 of them. So I have to distribute these 3 stars in these places. Okay, so I have to arrange 4 bars and 3 stars. And the number of such strings with 4 bars and 3 stars will be 4 plus 3, 7. And I have to choose 3 positions for star. That will give me 7C3. Okay, fine. So now let's go to the next example. I'll give you some, try this out. Maybe I'll give like say 3 minutes.
Hello.
Yes.
Yes, sir. Sir, actually, in the previous problem,
Which one? This one? This one?
yes, sir, that cookie problem.
Ah,
Sir, we are choosing 3 cookies from 5 different cookies.
right.
So,
You can, okay, you can
two-
also choose 2 cookies of the same type.
okay.
Multiple cookies of the same kind can be selected. Was that the question?
No, sir, actually, here I am thinking the result would be 7C2.
Okay, why?
Okay, 5 different kinds of cookies are there.
Yeah. So why? What is the?
Sir, I thought that 5 cookies are of similar kind.
No, 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 no. 5 different kinds of cookies. So it's like a $10 bill, $20, 30. I mean, $50. It's like cookie 1, cookie 2, cookie 3. It's the same idea. Instead of, so previously here there was a $10, I mean 10 rupee. Now it's cookie 1 in that place. And within the same type, the cookies are identical. Let's say like two $10 bills are of the same type. 2 cookies of the same type are identical. Is that
Okay.
yeah?
Okay, sir.
Good.
Understood.
Okay. So yeah, so I get many answers for this problem. So this is once again, okay, so how many solutions does this thing have? It's the same star bar idea. So how do you do it? It's like, see, you can, okay, maybe I'll do it like this. See, suppose, I mean, I want, so let's say I have 15 stars. Okay, then I have to, and I want to allocate some number of stars to x1, some number of stars to x2, and some number of stars to x3, so that the sum is 15. So since I have 15, okay, so that is like saying I have two bars. I can either put, I can put some number of stars here, some number of stars here, some number of stars here. So each such picture gives a solution, and each solution gives such a picture. Okay, so it's the question of finding the number of such strings. So how many of them are there? There are 17 positions, and you have to choose two positions for the bars. So it's either 17C15 or 17C2. Okay, so I got several answers, but so some of you who have given a different answer, can you tell me if you have understood this?
Sir, should it not be 16 possible integers, because 0 is also a possible selection?
It will be taken care, no? Like if I have, see, for example, if I, for example, I can put all my 15 stars here.
We will have 16 stars in that case.
No, there are 15 stars only. If I don't put it here, I mean, if I don't put it here, it means it's 0.
Okay, okay, right.
Okay, good. Okay, any other question? No, it's assumed as non-negative, so 0 is allowed. Oh, okay. So if you, I see, some of you might have assumed that it's okay. Okay, so I proceed. You get back to me later if you have any questions. Okay, good. So here is a summary of permutations and combinations. Okay, so if repetition is, oops, sorry. If repetition is not allowed, so I'm assuming that I have n different objects. Okay, and then if I want to count the number of r permutations of it, I have to order r of them. That was npr with no repetition allowed. Okay, but if I want to arrange r of them with repetitions allowed, I have n into n into n into n r times, so n power r. This is permutations. Now suppose I don't want to arrange them in order, I just want to select them. Okay, now if I just want to select r objects out of n objects, that is just where repetition is not allowed. It's like, okay, so then that is ncr. But when repetition is allowed, that is, I have to choose r things, but I can take the same thing multiple times. So then you have to do the star bar business. You will have to put n minus 1 bars for the n objects and then distribute r stars. Okay, so just keep this picture in mind. Shall I continue? Just say yes if you are comfortable, reasonably comfortable so far, so
Yes,
that
sir.
I know. Yeah. Okay. Okay. Good. Okay. Good. Yeah. So all of this is there in the book. So in case you have missed some parts of this, please take a look at the book and solve some examples, and then it will become clearer. Okay. So then I go to, oh, okay. Let us see some other example. Just try this out, please. Okay, so yeah, there are some correct answers. So here you go. Okay, see, how can you, so what is the, so there are several ways of looking at the answer, but I'll just explain one possible way, which is, see, first of all, I have, look at the letters. Success, it has 3 S's, 1 U, 2 C's, and 1 E. Okay, and now I want to form words out of this. Okay, now, so the words will be of length what? 3, 4, 6, 7. There will be 7-letter words. Okay, now you can think of arranging these things as, I first choose positions for S. Okay, so that can be done in 7C3 ways. So then after I choose my positions for X, for S, I choose positions for U. Okay, so there are remaining 4 positions and I have to choose 1 position, so it's 4C1. Then I'm choosing positions for C, which is, there are how many positions left? So 3 plus 1, 4. There are 3 sorry, how many positions are left? So it should be 3C2, because there are 3 positions and okay, 1 second, did I make a mistake here? Wait, wait, wait. 1, 2, 3, 4, 5, 6, 7. So first I choose 3 positions for S, so that gives me, so that is gone, so that I'm left with 4 positions, and from 4 positions I choose 1 position for U, then that leaves me 3 positions. Then from 3 positions I choose 2 positions for C. Okay, that is 3C2, and then finally I have 1 C1. Okay, so, and then if I manipulate it, what do I get? 4C1 into 3C2 into 1, I should be getting a, okay, 9 factorial. This is what? 4 factorial into 3 factorial. This is 4 factorial. Ah, so I messed up here.
Sir, the lower part is not visible.
Oh, is it? Is it better?
No, it's not.
Is it like that for everyone? Like,
No, it's visible for me.
On the lower tab comes up automatically sometimes, so that's why.
It's visible, sir.
okay, okay. So anyway, I will, let me copy this and open it in a new. One second, one second. So I had this. Okay. So then I had to just manipulate it. So I will get, what is this? 7C3 into 4C1 into 3C2 into 1. This is 7 factorial by 4 factorial, 3 factorial. This is 4 factorial by 3 factorial into 1. This one, I made a mistake here, which should be 3 factorial by 2 factorial into 1 factorial, and then this thing. So then things will get cut, and I should get 7 factorial by 3 factorial into 2 factorial. Okay. So there are different ways of looking at it also. You can just arrange it and divide the permutations that are counted several times. And then you will be dividing each time by, so I mean, so you arrange success, but you know that there are how many, there are 3 C's. The C occurring, C here, C here, and C here will be counted thrice. No, sorry, it will be counted 6 times, because if I number them as C1, C2, C3, C1, C2, C3, C2, C1, C3, all of them will be counted differently, whereas they are of the same type. So then you divide by 3 factorial. Then from the remaining, you look at the same argument for S and for how many successes? 3 S's, and the same thing. No, no, that's all. Only S and C are repeating. So you will get 7 factorial by 3 factorial into 2 factorial. Yeah, sorry, this was S. Anyway, no, this is for some people who gave this directly. But do you understand this argument? Like I am choosing out of the total number of positions. I first choose positions for S, then I choose positions for U, then I choose positions for C, then I choose position for E. You can do it in any order. The final answer will be the same. Okay. Good. Okay. So now let us go to a, what is this? So let's like kind of generalize this. So I have, no, I think I made a, why did I write? Correct. So I want to permute n objects where n1 are of one kind, n2 are of a different kind, and nk are of a different kind. So in the previous case, I wanted to permute SU, CC, E, SS, right? So here there were 3 S's, 2 C's, 1 E, and 1 U. And in this case, in how many total number of ways can you permute? It's n factorial by n1 factorial times n2 factorial times nk factorial. You will get this as your solution. Okay. So far so good. So far we have seen permutations, combinations where repetitions are allowed, and now we are looking at permutations where some number of objects are of one kind, some number of objects are of different kind, and so on. So okay. Uh, is there any question up to now? Because then I'm going to the next topic. Okay, so if you can also ask me towards the end. Okay, so let me go to another problem, which is distributing objects to boxes. So try this question, please. So it's 410. Maybe like 5 minutes. And before that, if several of you answer, I'll restart. Okay. So this question, yeah, boxes can be empty. Yeah.
Hello, sir. Are you there?
Yes, tell me.
Sir, how the boxes can be empty? So box 1 contains 3 objects, box 2 4 objects. So
Oh,
total
I'm sorry.
they are summing
Yeah,
up to 10
sorry, sorry.
distinct.
Yeah, you're right. Yeah. Sorry. I did not. I answered a bit quickly. Yes. So you have to place 10 objects in this particular manner. Yeah. You're right. Sorry. Yeah. Okay. I think now it's time to explain. So yeah, several of you have the right answer. So essentially, how do you look at this? So there are 10 objects. Okay, and then how many boxes? There are 4 boxes, and with this criterion. Okay, so 3 objects should go to box 1. Okay, so I can say, let's say 3 objects should go to box 1. Okay, and then 4 objects should go to box 2. So let me put box 2, box 2, box 2, box 2, say, and box 3 contains 1. So 1 object should go to box 3 and 2 should go to box 4. So what I did here, so I looked at those objects. I was assigning to every object a box number. Okay. So now the question is, in how many ways I can do this? So you can think of this as, suppose I give you this string 2, 3, 1, 2, 1, 2, 1, 2, 4, 4. It's like the word success. And in how many ways can I rewrite it? Okay. And then what was the answer? It was like there are 10 factorial by, finally I will get 10 factorial by, so 1 comes 3 times, 2 comes 4 times, 3 comes 1 time, and then 4 comes 2 times. So essentially it is the same as, so first I choose 10C, for 1 I choose 3 positions, then I choose 4 positions for 2, this and then I choose out of the remaining 3 1 position for 3, and then 2C2. Okay, it's the same as the previous question. So you just have to look at it in this form. Okay, so is this clear? I mean, several of you have given the answer, so I believe it is clear. If you have any questions, you can check with me later. So this is, so in general we have this problem of distributing distinguishable objects. So they were object 1, 2, 3, 4, 5, and so on, into distinguishable boxes, box 1, box 2, box 3. And in which case, using the argument before, to every object you associate a box number. So then I have n1 ones, n2 twos, n3 threes, and nk k's to be arranged. And that gives me n factorial by n1 factorial into n2 factorial into so on till nk factorial. So this is the number of ways in which n distinguishable objects can be distributed among k distinguishable objects, such that box 1 contains n1, box 2 contains n2, and so on. Okay. Now, okay, fine. We make a small change. Now I want to place 10 identical balls into 6 different boxes. Try this question out. So again, I'll give around 5 minutes.
So this time the empty box is allowed, or Other.
Yes, yes, yes. Now boxes can be empty.
Okay.
Okay. So let's see the answer. Okay. So I have 10 identical balls, and then I want to place it in 6 different boxes. Okay. So how do I go about this? So I have box 1, box 2, box 5, and box 6. Okay. And then I have to place 10 identical balls. Okay. So either I place, say, 3 balls here, then 2 balls here, 1 ball here, and then I'm left with what? 3 plus 2, 5, 6, and then maybe I just place 4 here and 0, 0 here. Or I can do, 1 here, 2 here, so on, such that the sum is 10. So in general, if I say there is x1 balls here, x2 balls x3, x4, x5, x6. I want to find the number of solutions to, so we want to find number of solutions x1 plus x2 plus x3 plus x4 plus x5 plus x6 equals 10. And this we did just a while ago, okay, using stars and bars. I mean, you can look at it in another way also, like I have 5 bars and I have 10 stars. So I will do the star picture for this previous distribution. So there'll be 3 here, 2, 1, 4, and nothing. This is the previous arrangement. So it's like I have to count the number of such strings, and then we have seen how to do that. So there is what? There is 5 bars and 10 stars, and then I have to choose 5 positions for the bars. So the answer will be 15C5. Okay. So is this part clear? Yeah, several of you have given me the right answer. Yeah. Okay, good. Okay, good. See, what is the difference between the previous problem where we were distributing n different objects into k different boxes? So now we are interested in n indistinguishable objects, that is identical objects, into k distinguishable boxes. And in that case, when the objects are identical, you look at them as stars, identical stars. And then you put k minus 1 bars, and totally you have n plus k minus 1 things, out of which you have to choose k minus 1 positions for the bars. So this is the same as arranging k minus 1 bars and n stars. Okay, and that gives me this. So far we have seen two things: distributing different objects to different boxes, distributing identical objects to different boxes. Now the natural question is, what about distributing objects into identical boxes? Okay, so this I'm not going to do. Okay, so you can read the book if you are interested. Okay, for the moment, just assume that we will consider distribution where boxes are distinguishable. Okay, so actually I'm done for the day to make up for the too long first 2 lectures. So just to summarize what we have seen, so to this class we have seen permutations with repetitions, combinations with repetitions. So remember that table that was shown. If repetition is allowed, if repetition is not allowed, remember that table. Then the next thing that we saw was, remember that example with success, where we have permuting some total number where some number of them are identical. And then finally, we saw 2 things, which is distributing objects to boxes, where boxes are distinguishable. And in the first case, we got a formula which is the same as this. And in the second case, we got a formula which is the same as this. So this and this were same, and this were same. Okay. So go through this once again, try a lot of problems. So we have fixed teaching assistants for your course. So they will soon contact you. Maybe they've already contacted you. So has someone contacted you regarding tutorial 1? Okay, good. Okay, so try out the problems and then you can attend the tutorial session if you have any questions. Okay, so the class is over. I will stay back for some 5 to 10 minutes if you have any questions. Okay, but if you have understood things, you feel free to leave. Yeah.
Excuse me.
So the tutorials are not going to be graded. Yeah.
So one thing, this last question which you were saying, I got your approach and I understood that very well. But before knowing this approach, there was one thing in my mind that, say, the first box can be filled in 10 different ways, right?
Yeah,
Because
yeah,
we have 10 boxes.
yeah.
The
So
same goes for the second box and so on. Like, can you correct me, like,
yes,
why, where am
yeah.
I wrong in this?
See, the balls are identical. Okay.
Hmm.
Now wait. So you said 10 power 6, no?
Yes, yes.
So and what was the thing? So you say box one. So how do you go about it?
This could have 10 boxes, 10
Sorry,
balls.
sir.
Right, because they're like 0, 1, 2, 3 till up to 10. It has 10 options.
Well, first of all, with zero, it has 11 options. But no. So what was your? I think you had a different argument to get to 10 power 6.
Like every box has the same number of options to be filled, now.
See,
Like
if
I
my
thought this
balls
is
were
wrong.
numbered,
I
okay?
know this is wrong, but I don't know where exactly it is
No.
wrong.
So if the balls are numbered,
Huh.
okay, then putting ball one here, ball two here, ball three here. Assume there are only three balls. Okay. So ball one, ball two, ball three is different from ball two here, three here.
Hmm.
Okay. So I think what you should do is you take a smaller number,
Huh.
okay, and then just distribute them explicitly and see where you're going wrong. So instead of 10 identical balls into 6 different boxes, maybe you just take, I don't know, 3 identical balls into 2 different boxes. Maybe we can do that.
Okay.
And
Can I
then see,
answer?
yeah, tell me.
Uh, yeah, first of all, correcting that it should be 11 to the power 6. You're correct about that. Huh? But in that, as it assumes that every box has 11 options. So
Hmm.
if you fill the first box with, say, 5 balls, then the second box does not have 11 options. It has 6 remaining
Yeah,
options.
of course. Yes,
So
yes.
Yeah.
there is a lot of double counting in that method.
Okay. I think I'm double counting in that. If
You're
uh,
double counting a lot of things basically.
yes, yes.
So the
Yeah.
first box is true that it has 11 options. The
Hmm.
second box's options depend on what the first box's options were. So there will be multiple cases and counting them is very hard in this case. Maybe in the case of 3, it might be easy. But as the numbers grow larger, it will become tougher and tougher.
Yeah.
Yeah, I understood, sir. Maybe I was double counting. Like this is a valid thing. I think I
Yes,
was
yes,
double
yes.
counting.
You're right.
Right. Okay. Yeah.
Thank
Thank
you.
you.
Who was it? Shubham?
And thank you, sir.
Yeah, it was me.
Thank you. Okay. Any other questions?
Hello, sir.
Yes.
Okay, sir. In the same question, you have this equation right at the bottom,
This
x1
one?
plus
Yeah.
yeah, and uh, what happens if the x1, x2, etc. can't take the value 0? How many solutions would there
So
be?
this is a different problem. Okay.
Can
So
we do it with the bars and stars?
so you first assign. So they have to start with at least one, right?
Yeah,
So what is the exact question? So I have
if,
x1,
if
so
an
number of solutions which are positive.
positive and can't be 0. Yeah, okay,
Correct. So suppose I assign 1 1 1 1 1 to them. For
okay,
sure, I have to have 1 1 1.
okay.
I am left with what? I am left with, so this is already 6. I'm left with 4. Okay. And this 4 needs to be distributed among these 6.
Yeah.
Okay. So then I want to find the number of solutions to x1 plus x2 blah 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 plus x6 equal to 4.
Oh,
Yeah, but they are non-negative.
yeah. Okay.
Okay, so you just have to subtract some part from this side.
I'll try that.
You just have to subtract this minus the minus 6.
Yes, sir. Yes, sir.
Okay.
So in the
Yes.
same question,
Hmm.
uh, I am unable to convince myself that 6 to the power 10
Okay, now 6 to the power 10.
is uh, mm, double
See,
counting something or not
yeah.
giving
So
the
this
right answer.
I kind of thought this is what Prasun was doing, in the sense like so somewhere you are doing some functions. So 6 into 6 into, so like you this is what I thought you're doing this. So ball 1, you're associating which box?
Yeah, ball one has 6 options
6
to
options.
get into, and similarly, all the
Ball
balls have
2
six
has, yeah,
options
correct,
to get into.
right? So what goes wrong
But
here?
mhm.
Because you're doing ball 1, ball 2, ball 3, and so on. They are not different. Okay, so let's look at it this way. So let's take 3 balls and say 2 boxes. Okay, now how can I distribute them? So either I put 3 comma 0, that means box 1 has 3 and box 2 has nothing. 2 1 1 2 0 3, right? Are
Yes,
you with
sir.
me? Okay.
Yes, sir.
But in your method, what you would do is, so you will number the balls 1 2 3. Okay, and then you will sorry about this. Okay, so what you will do is you will say 1 goes to, I'll put some other color for box. You will say 1 goes to box 1, 2 goes to box 1, 3 goes to box 1. This is one thing. Okay, no, let me not, let me take a different thing.
Yeah, I got it. So, for example, if the second box contains first and second, or the second ball contains first and third, but in my case, it is
Exactly.
having a different counting, but in the
Absolutely.
indistinguishable case, it will not.
Exactly. Yeah, absolutely.
Yeah. Thank
Okay.
you, sir.
Good, good, good. So let me just put it down. So to this thing, okay, and then 1 2 3, this goes to 1, this goes to 1, and 2 goes to 2, will be counted differently when balls are distinguishable. Okay, any other questions? Okay.
Thank you, sir.
Okay, good. I'll stop sharing. Okay, so there are no questions, so see you next Tuesday then. Bye.